Welcome to Astronomy Daily, your source for the latest space and astronomy news. I'm Anna.
And I'm Avery. We're here to bring you today's cosmic headlines on this Wednesday, February 4th, 2026.
We've got a packed show today with some significant developments. NASA's Artemis 2 mission has hit another speed bump, with their moon rocket experiencing some familiar issues during testing.
SpaceX is making headlines on two fronts today, launching an innovative new space safety system while also dealing with a temporary grounding of their Falcon 9 rocket.
The James Webb Space Telescope has spotted something extraordinary in the early universe, a rare five-way galaxy merger that's challenging our understanding of cosmic evolution.
Scientists have finally cracked a 50-year mystery about why nearby galaxies seem to be fleeing from us, and it involves a massive cosmic void.
And we'll wrap up with fascinating new research on runaway stars, massive stellar objects racing through the Milky Way at incredible speeds.
Let's dive in.
Our top story today comes from NASA's Kennedy Space Center in Florida, where Artemis 2 mission has been delayed by at least a month following issues during a critical wet dress rehearsal test.
This is the mission that will send 4 astronauts on a flyby of the moon, the first crewed lunar mission in over 50 years. The crew includes NASA astronauts Reid Wiseman, Victor Glover, Christina Koch, and Canadian Space Agency astronaut Jeremy Hansen.
So what happened during this test? NASA concluded a 49-hour practice countdown on Tuesday after loading 700,000 gallons of liquid hydrogen and liquid oxygen into the massive Space Launch System rocket.
And early in the tanking process, as we reported yesterday, they detected a hydrogen leak from the interface that routes cryogenic propellant into the rocket's core stage. Sound familiar?
Unfortunately, yes. These hydrogen leaks are reminiscent of the issues that plagued the Artemis 1 launch attempts back in 2022. However, there's some good news. They did resolve the issue during this test and actually achieved full tanking on the first try, which NASA considers a tremendous success.
That's actually quite significant progress. The resolution involved stopping the hydrogen flow, allowing the interface to warm up so the seals could reseat, and then adjusting the flow of propellant. It worked, but it raised concerns about launch day operations.
NASA Administrator Jared Isaacman announced they're moving off the February launch window and targeting March for the earliest possible launch. The first opportunity next month is Friday, March 6th at 8:29 p.m. Eastern Time, with the window extending through March 11th.
There were other issues too, weren't there? I read about problems with a valve and some communication dropouts.
Right. A valve associated with the Orion crew module hatch pressurization had to be retorqued, and closeout operations took longer than planned. Cold weather affected several cameras and other equipment, and perhaps most concerning, there were dropouts in audio communication channels that have been recurring over the past few weeks.
What's the crew saying about all this?
Commander Reid Wiseman posted on social media expressing immense pride in seeing the rocket reach 100% fuel load, especially knowing how challenging the scenario was for the launch team. He said they're jumping back into training tomorrow to start preparations for March.
And NASA's planning another wet dress rehearsal before the actual launch, correct?
That's right. Launch Director Charlie Blackwell Thompson confirmed they'll conduct another wet dress before proceeding with the actual launch. The team needs to fully review all the data from this test, mitigate each issue, and return to testing before setting an official target launch date.
It's a delay, but safety has to come first, especially with a crewed mission to the moon.
From the moon to low Earth orbit, SpaceX has just unveiled a revolutionary new space safety system called Stargaze that could fundamentally change how we manage the increasingly crowded space around our planet.
This is fascinating technology, Anna. Stargaze is a space situational awareness system that uses data from nearly 30,000 star trackers across the Starlink satellite constellation to continuously monitor objects in low Earth orbit.
30,000 star trackers. That's an incredible network. And they're detecting approximately 30 million transits daily across the fleet. That's a several order of magnitude increase in detection capability compared to conventional ground-based systems.
The need for this kind of system has never been more urgent. Practices like leaving rocket bodies in LEO, operators maneuvering satellites without sharing trajectory predictions, and anti-satellite tests have all heightened collision risks. Conventional methods typically observe objects only a limited number of times per day, causing large uncertainties in orbital predictions.
What makes Stargaze particularly powerful is that it provides conjunction screening results within minutes compared to the current industry standard of several hours. That speed can be the difference between a successful collision avoidance maneuver and a catastrophic impact.
SpaceX actually shared a real-world example that demonstrates just how critical the system is. In late 2025, a Starlink satellite encountered a conjunction with a third-party satellite that was performing maneuvers, but whose operator wasn't sharing ephemeris data.
Ephemeris data, that's the trajectory prediction information, right?
Exactly. So initially, the close approach was anticipated to be about 9,000 meters away, considered a safe missed distance with zero probability of collision. But then, just 5 hours before the conjunction, the third-party satellite performed a maneuver that collapsed the anticipated missed distance to just 60 meters.
60 meters? That's terrifyingly close in space terms.
Stargaze quickly detected this maneuver and published an updated trajectory to the screening platform, generating new conjunction data messages that were immediately distributed. The Starlink satellite was able to react within an hour of detecting the maneuver, planning an avoidance maneuver to reduce collision risk back down to zero.
And here's the really important part. SpaceX is making this data available to all satellite operators free of charge. Starting this spring, satellite operators who submit their own trajectory predictions to the platform will receive conjunction data messages against Stargaze data.
It's been in closed beta with over a dozen participating satellite operators, and the response has been positive. SpaceX is drawing a parallel to commercial aviation. There are hundreds of thousands of sites daily, but they avoid collisions because they broadcast their location and flight plans to other aircraft.
SpaceX is calling on all spacecraft operators to follow this same minimal standard of sharing predicted trajectories. Starlink updates and shares their ephemeris publicly every hour, as an example.
This is the kind of collaborative approach we need as space becomes more congested. It's not just about protecting SpaceX's massive constellation, it's about creating a safer orbital environment for everyone.
Speaking of SpaceX, the company has temporarily grounded its Falcon 9 rocket following an issue with the upper stage on a recent Starlink launch, and the timing couldn't be more critical.
This happened on Monday, February 2nd. A Falcon 9 successfully delivered 25 Starlink satellites to low Earth orbit as planned. But after deploying the payloads, the rocket's upper stage failed to perform its deorbit burn.
That deorbit burn is designed to bring the spent upper stage down for controlled destruction in Earth's atmosphere. Without it, we have another piece of debris in orbit, exactly the kind of problem that Stargaze is designed to help monitor.
The good news is the upper stage did manage to passivate itself by venting propellant, which lowered its perigee to about 110 kilometers. According to satellite tracker Jonathan McDowell, it will re-enter quickly.
But SpaceX has grounded the Falcon 9 fleet while teams review data to determine root cause and corrective actions. And here's where the timing gets tricky. The Crew 12 astronaut mission to the International Space Station is currently scheduled to launch on February 11th, just 8 days from now.
Crew 12 is particularly important because it will restore the ISS to its normal complement of 7 crew members. The station has been operating with a skeleton crew of just 3 astronauts since January 15th, when the 4 Crew 11 astronauts departed in the first ever medical evacuation from the ISS.
NASA Associate Administrator Amit Kshatriya confirmed that NASA teams from the Commercial Crew Program are embedded in the investigation alongside SpaceX and the FAA. He said they're pressing towards the Crew 12 window, but the launch will be contingent on the return to flight rationale.
It's worth noting that the Falcon 9 has an incredible safety record. Last year alone, it launched a record-breaking 165 times, with all missions successful. Just a single mission experienced a significant anomaly, a Starlink launch where a booster toppled after landing at sea.
That March 3rd incident was traced to a fuel leak in one of the booster's 9 Merlin engines, which led to a fire that weakened a landing leg. SpaceX halted launches for a week at that time as well.
The question now is whether they can resolve this upper stage issue quickly enough to meet the February 11th Crew 12 launch date. If not, those 3 astronauts on the ISS will have to wait a bit longer for reinforcements.
From orbital mechanics to the deepest reaches of space, the James Webb Space Telescope has spotted something extraordinary, a a five-way galaxy merger in the early universe that's challenging our understanding of cosmic evolution.
This is remarkable, Anna. The system consists of 5 compact, actively star-forming galaxies that were merging when the universe was only about 800 million years old. That's just 6% of the universe's current age.
And the level of complexity is what's really stunning astronomers. These 5 galaxies are packed into a remarkably small region of space. They're separated by only tens of thousands of light years. To put that in perspective, that's far closer together than most neighboring galaxies in the modern universe.
Dr. Wada H.U. from Texas A&M University, the study's lead author, explained that what makes this remarkable is that a merger involving such a large number of galaxies was not expected so early in the universe's history. At that time, galaxy mergers were thought to be simpler, usually involving only 2 to 3 galaxies.
But it's not just the number of galaxies that's impressive. These 5 galaxies are producing stars at a combined rate of roughly 250 solar masses per year. That's far exceeding typical star formation rates for that era.
And this rapid stellar production has already enriched the system with heavier elements like oxygen, materials forged in stellar interiors and dispersed through galactic interactions. The presence of these elements indicates that multiple generations of stars had already lived and died.
The really fascinating part is that gas containing oxygen and hydrogen extends beyond the galaxies themselves. This suggests that gravitational interactions are pushing enriched material into intergalactic space, showing how early mergers may have shaped not just galaxies, but the larger cosmic environment.
This discovery really disrupts the standard model of galaxy assembly. That model proposes a gradual buildup where small galaxies merge over long periods to form larger systems. But this 5-way merger demonstrates that complex multi-galaxy interactions were already underway less than 1 billion years after the Big Bang.
Professor Casey Popovich, a co-author on the study, emphasized the implications. By showing that a complex, merger-driven system exists so early, it tells us our theories of how galaxies assemble and how quickly they do so need to be updated to match reality.
This adds to the growing body of evidence from JWST that the early universe was capable of producing massive, mature-looking galaxies at astonishing speed. Matter in the early universe appears to have clustered more rapidly and efficiently than our simulations suggested.
The study was published in Nature Astronomy, and it's another example of how JWST is fundamentally changing our understanding of the cosmos.
Sticking with cosmic mysteries, scientists have finally solved a 50-year-old puzzle about why nearby galaxies appear to be fleeing from our own Milky Way. And the answer involves a massive cosmic void right in our neighborhood.
This is one of those mysteries that's been nagging at astronomers for decades, Avery. Most large galaxies near the Milky Way, with the exception of Andromeda, appear to be moving away from us and seem largely unaffected by the gravitational pull of our local group of galaxies.
The local group being the Milky Way, Andromeda, and dozens of smaller galaxies. So what's the solution?
Led by Ewood Wempe at the Kapteyn Institute in Groningen, an international research team used advanced computer simulations and discovered that matter just beyond the local group forms a broad, flat structure stretching tens of millions of light years across. And here's the key: vast empty regions lie above and below this structure.
So we're basically living on a cosmic pancake surrounded by voids?
That's actually a pretty good analogy. This flat distribution of matter is the only way to accurately account for both the combined mass of the Milky Way and Andromeda and the unexpected motions of nearby galaxies.
But how does this flat structure explain why galaxies are moving away from us?
It comes down to the local void, a vast empty region discovered back in 1987 by Brent Tully and Rick Fisher. The local void extends approximately 60 megaparsecs, or about 200 million light-years, beginning at the edge of the local group.
The local void is growing because there's very little matter inside it to exert gravitational pull. Our Milky Way sits in what's called the local sheet, a flat array of galaxies that bounds the void. And this local sheet is rushing away from the void's center at 260 kilometers per second.
How fast is that affecting the Milky Way?
The Milky Way's velocity away from the local void is 970,000 kilometers per hour. That's 600,000 miles per hour. It's astonishingly fast.
So the new simulations show that this hidden geometry, the flat plane of dark matter beyond the local group with voids above and below, is what's driving these galactic motions?
Exactly. When researchers included this configuration in their simulations, they closely matched the observed positions and speeds of nearby galaxies. It provides a coherent explanation for motions that have puzzled astronomers for half a century.
This is connected to research about the Hubble tension, too, isn't it? The discrepancy in measurements of the universe's expansion rate?
That's right. Some researchers have proposed that if we're inside a large local void, it could affect how we measure cosmic expansion, making the local universe appear to be expanding faster than it actually is. Though that particular idea remains controversial and needs more evidence.
What's remarkable is that we're learning our immediate cosmic neighborhood is far more structured and dynamic than we previously understood. We're not just floating in a uniform sea of galaxies. We're on a sheet of matter bordering a massive void.
And that void is shaping our galaxy's journey through space in fundamental ways.
For our final story today, we're turning to some of the fastest objects in our galaxy, runaway stars that are racing through the Milky Way at incredible speeds.
Researchers from institutes across Spain have just completed the most extensive observational study to date of these stellar speedsters, analyzing 214 O-type stars, the brightest and most massive class of stars in our galaxy.
These aren't just fast-moving stars, Avery. We're talking about stars with velocities that often exceed 700 kilometers per second. That's fast enough to escape the Milky Way's gravity entirely.
The term runaway stars was first used back in the early 1960s by Dutch astronomer Adrian Blau. He observed stars moving at unusually high speeds and proposed they originated in binary systems and were ejected when the companion star collapsed and exploded in a supernova.
By 2005, astronomers discovered even faster runaway stars, leading to the designation hypervelocity stars. These objects are fascinating because of the influence they have on galactic evolution.
By escaping their systems of origin, these stars irradiate gas and dust in the interstellar medium, eventually seeding it with heavy elements after they go supernova. This affects how future stars and planets will form.
So, what did this new study reveal? The team used data from ESA's Gaia Observatory and the IACOB spectroscopic database to analyze these 214 O-type stars.
They found that most runaway stars rotate slowly, while those that rotate faster are more likely to be linked to supernova explosions in binary systems. And here's an interesting finding. The highest velocity stars tend to be single, suggesting they were ejected from young clusters through gravitational interactions.
So there are actually two different mechanisms creating runaway stars?
Exactly. Some are explosively ejected by supernova in binary systems, while others are gravitationally ejected from close encounters with star clusters. The study helps clarify the relative contributions of these two mechanisms. Lead author Mar Carretero Castrillo, now at the European Southern Observatory, called this the most comprehensive observational study of its kind in the Milky Way. By combining information on rotation and binarity, they're providing unprecedented constraints on how these runaway stars are formed.
The team also identified 12 runaway binary systems, including 3 X-ray binary sources that contain neutron stars or black holes, and 3 additional systems that are likely candidates for hosting black holes.
Perhaps the strongest evidence for multiple ejection mechanisms was this. Virtually no stars in the study exhibited both high velocities and rapid rotation. If all runaway stars came from the same process, you'd expect to see some with both characteristics.
Future Gaia data releases and ongoing spectroscopic studies will help astronomers trace these stars back to their birthplaces within the Milky Way, which will confirm which mechanism was responsible in each case.
And there might be another fascinating angle to this research. Understanding these systems could shed light on another role they may play in galactic evolution, potentially distributing the basic ingredients of life throughout the Milky Way as they travel.
Cosmic messengers carrying the seeds of life across the galaxy. That's a beautiful thought to end on.
And that wraps up today's episode of Astronomy Daily.
From NASA's moon mission delays to SpaceX's new safety innovations, from ancient galaxy mergers to mysteries in our cosmic neighborhood, it's been quite a journey through the cosmos today.
Thanks for joining us. For more space news, visit our website at astronomydaily.io, where you can explore our full archive and stay updated on the latest cosmic discoveries.
You can also find us on social media at Astro Daily Pod across all major platforms. Until next time, keep looking up.